Good morning. Thank you. So, as it was introduced, I'm Modrate, PowerPhotonic, and I'm here to talk about how laser welding can be improved by freeform beam shaping optics. A little bit first about PowerPhotonic. So we're a micro-optics manufacturer, head office based in Dalgety in Scotland. In the previous slide, that was a snowy picture. And then we also opened a new site in San Rita in Arizona, which was the sunny picture in the previous slide in 2022. Over both of the sites, we've got 55 staff, and we've been manufacturing optics since 2004, which means that this year is our 20th birthday. To celebrate the milestone, we had several little events in Edinburgh, and those cupcakes tasted much even nicer when you look at the picture. So, as I said, I'm going to talk about freeform beam shaping and how it's used to enhance laser welding. For laser welding, it's important, has important requirements. So, strength is very important, the precision of the weld is very important, and how efficient it is, because we want to turn around these cars really quickly and the batteries. But there's a lot of challenges as well with laser welding. So you've got spatter, differences in material. So for instance, you could be trying to weld copper to aluminium. You get quite a lot of cracking, brittleness and porosity. The way that we manufacture our beam shaping optics to help this is using a direct fabrication using a laser also. So we use laser machining process which ablates a gross optical form on the surface of fused silica, and it's always fused silica. That ablates a net, you can see there in that picture, the net shape point by point. And then we use the same laser to go back over and reflow the surface, so it takes it back to the bulk fused silica, and it creates an ultra smooth optical surface, which gives very low roughness, very low scatter, and really high efficiency, which means it can be used in high power welding, but also it can be used in low power welding as well. But the reason we can get our different beam shapes is because the fabrication that we can do with our technique is truly freeform. Laser welding can be optimized in several different ways. You can change your laser power, so high power, low power. You can change your wavelength, so there are near infrared welding. You also have green welding, blue welding. You can change your mode of laser, so you can have a multi-mode laser or a single mode laser, or you can have a pulse laser or a continuous laser. Other ways are you can change your beam delivery, which could be your spot size, your focal length, all of your optical system. You can change the speed of your weld. One of the most common things in welding is to add wobble, or you can change the spot size. However, what we were going to talk about today is how you change the shape of the spot, the intensity. This shows the intensity profiles of the different spot shapes. So you start obviously with a Gaussian, and then the next one is a flat top, which is used a lot of welding, or a ring shape, or the one second from the end is a ring core, which will be discussed quite a lot in this talk. And then we have a tail shaper, which is something that we developed ourselves at PowerPhotonic. These are, as a little picture, of our different possible welding beam shapes that was thought up by Dr. Alex Griffiths. So as you can see here, you've got rings and cores, you've got what we call a tail shaper, which has got a hot spot at one end. You can even have hot edges. You can have a flat top with a spot that's a hot spot in the middle that's square, round, and you name it. But the most important ones we're going to talk about today is the core and ring and the tail shaper. This is PowerPhotonic's core and ring beam shaper. So this beam shaper creates a core and a ring profile at the focus, but also all the way through caustic. It's the way that it works for welding is the central core of intensity creates the keyhole weld, and then the surrounding ring then influences the milk load, so it helps with the spatter. It's got many customizable parameters. You can change the ring size, and you can change the core size, and you can change the core to ring intensity ratio. This is the measure data that we have from our optic. So as you can see, the coded ring all the way through cosec. This is actually both of these. One is a 900 micrometer ring and the other one's a 1200 micrometer ring. But the power ratio for both is 50-50, and it's, looking at it this way, it doesn't look like it is, but it has exactly the same power ratio around the outside as it before. As I mentioned before, we also have our one of our own ideas, Alex Griffiths, the big engineer, came up with, and it's a tail shaper. So it can have a hotter end, so it can be the front or the back. We're probably going to talk about the front one mostly, and this is the back one here. It's an asymmetric profile, and it always matches the direction of the weld. The primary spot provides the power to generate the keyhole that I mentioned before, that creates the milk hole, and then the tail that follows the main spot influences the thermal gradient, so helps with the grain direction. The tail shaper is also customizable, so you can change the length of the tail profile, the tail direction, and the primary spot size, as you can see, we've got bigger spots and smaller spots, even the spot shape, some are square, some are round, and the primary spot profile. This is the functional measurement as well for this. So in this, it shows that what we've modelled, it works. Its tail intensity is 30% of the overall relative to the primary spot. So I want to talk about a case study. PowerPhotonic worked with WMG at the University of Warwick, particularly Pascale and Sousa's team, on some welding of aluminium 6082. So it says autogeneous welding, so that means that it doesn't need to have a filler wire. So sometimes when you weld, you would put a filler wire in and use that to weld the two together. That's what we're trying to remove. Aluminium 6082 is a very common material for car bodies, but it's very sensitive to cracking, which makes it complex and a wasteful process. What we would normally want is for our beam shaper to go between the collimate lens and the focusing lens. But for the sake of research, it's much easier to replace the protective window as it's a modular system. So we would manufacture an optic that its geometry was the correct size for putting into that window. It goes in just before the collimate lens, and it's designed specifically to be there. And then WMG did some measurement and then also some welding using it. So this welding used no filler wire, no shield gas either, and only the laser. So I'm going to show you a video. So this is a video of the unshaped weld, and you can see that the grains are sort of less even. There's quite a lot of spatter. And in the picture along the bottom, you can see almost little lumps, and that's like air underneath. So if we then move on to our beam shapers added into that unshaped spot. So the first one is the ring and core. Again, you can see the grains are much more even. There's a lot less spatter. There is still a little bit of this, but it's a lot more even. And you can actually see on the picture below, there's none of those lumps. And then the tail shaper, which we like to show, is it's a nice smooth weld. You can see the grain direction. And again, at the bottom, there were lumps and bumps and air pockets. I haven't got the slides here, but there was some testing done to show that both of these welds caused a lot less cracking, there wasn't as many holes, it was much less porous. So the best way to show that for me today was to show you the tensile strength. So without those holes and cracks, the tensile strength was improved. So the weld shape with the welding with the unshaped spot was prone to cracking due to the central grain structure. So you saw that in the weld, and you can see that the tensile strength was just over half of the base material, but the core and ring, the 1,200 micrometer, and the front tail shaper took the base material, took the tensile strength back up to almost the base material. So, you know, it was a finer microstructure when we looked at it internally, and it had a much more favourable grain orientation, which I think was clear from the video. The conclusion to the project that was carried out is that beam shaping did optimise the laser welding performance. You can see here that our model and the measured were very similar, and then the applied also. PowerPhotonic beam shapers provide a freeform beam shape, so we can change what the beam shape looks like, and we can change what we want. As I said, you know, they're all customizable. Beam profiles can be tailored to influence the milk pool, size and shape and dynamics, and very happily we demonstrated a 40% increase in the weld strength of the beam shape. The next steps for us are to take all the learnings from that project and use beam shaping in a new innovative area at PowerPhotonic. We're looking to win along with cars, welding, and ionic, and WNG. It's called Sony Shape Laser, and it will take the learnings of the beam shaping and also ultrasound, which was another grant that was won before, and put those together and see if we can move the tensile strength up to back to the base. Also, we'll be working with collaborators and companies to develop some new beam shapes. Alex is always keen to develop new beam shapes and see how they work with welding. I'd like to thank Alex and Persephone who developed these optics, WNG, Dr. Gali for carrying out the welding, and also everybody